Good afternoon, one and all. I welcome you all for the parallel session at South 1. The topic is geosynthetics engineering. I would like all of you to welcome our chair and co-chair for today's session, Dr. Vikas Patil, chair for the session, Professor Ramakrishna Bag, co-chair for the session. Now I request Dr. Patil sir to please preside over the event.
That for thematic lecture that Castrona and Paula, they have not reported. We'll start with the next who is present, Nitish Kumar and Ramesh Kandaswamy. We'll start. This topic is evaluation of mechanical degradation to glass grid under cyclic loading during installation in roads. Thank you.
This one? Nitish. This usually is working, no? There is some. So good afternoon, everyone. I am Nitish Kumar. I am a PhD research scholar and in the Department of Civil Engineering, IIT Madras, working under the supervision of Dr. Ramesh Kannan. So I would like to thank the organizers for providing me this platform to present my research work on the evaluation of mechanical degradation to the glass grid under cyclic loading during installation in the road. So these are my research outline. So in this study, I am going to basically discuss about the damages induced in the grid during the installation and its quantification and examination using digital image correlation technique. So coming to the introduction, so as we all know, geo-reinforcement, which include geogrid, geotextile, geocells, have been extensively used in geotechnical engineering application, particularly for the roads and several other applications. We use this reinforcement because of its high mechanical performance, long-term durability, ease of installation, as well as cost effectiveness. So one of the biggest problem with this kind of reinforcement is the installation damages, particularly the localized damages in the reinforcement during the operational handling, transportation, as well as installation in the road. When we install this kind of reinforcement in the road, there is a chance of damages in the grid. So there are several studies which have been studied, and from those studies we have noticed that during the installation of the grids, the tensile strength can reduce up to 35%, as well as the tensile stiffness could reduce up to 25%. So how these damages happen? So when the reinforcements we use in the subbase and base layer of the aggregate and compacted using the roller or due to the movement of the vehicles over the surface, there is a chance that the ribs of the yarn may break, and that cause the reduction in the tensile strength. So it is important to quantify the percentage strength reduction due to this kind of movements of the rollers. So quantifying this percentage strength reduction in the field is quite difficult. So it is important to simulate the similar condition in the laboratory in order to quantify the strength reduction and installation damage factor. So basically these are my objective: to quantify the percentage strength reduction of the grid after cyclic loading, and to quantify the to do the image analysis to quantify and examine the localized damage occurred during the installation. So to achieve this objective, we are considering three different ranges of glass grid, which we have called GG1, GG2 and GG3. These grids are having different aperture, thicknesses and mass density. In addition to that, we are considering three different ranges of aggregate. And why we are considering this aggregate? Particularly these size of aggregates we used in the subbase and base course of the pavement. So we are using these three different ranges of aggregate and simulating the field condition in the laboratory. So to do that, we have designed our experimental setup. So this experimental setup consists of a steel box which is having two parts. In the bottom section, initially we filled with the aggregates we used for our study, and then place the reinforcement at the center of it, and then again fill the top layer with aggregates. This is the vertical cyclic actuator through which we can apply the cyclic loading.
Check.
Cyclic loading of 400 kPa amplitude, magnitude with 200 number of loading cycle at 1 Hz frequency. In addition to that, we use this tensile setup to quantify the strength reduction after inducing damage. So basically, once the cyclic loading will be completed with this set of experiment, we will carefully remove the specimen and do the tensile test with this. So for during the tensile test, we have the provision to the results and discussion section. So initially we have started with the intact tensile strength of the grid. So we have quantified the intact tensile strength before inducing any damage for all the three grids. So for GG1 grid, the tensile strength, maximum strength is 25 kilonewton per meter, while for GG2 and GG3 grid it is 50 kilonewton per meter. Next is our tensile strength of the damaged grid. It means it signifies that once the cyclic loading is completed with different ranges of aggregate, we have quantified its tensile strength. So as I have already said, we are using three different ranges of aggregate for three different grids. So in the first set of experiment, we use smaller aggregate, which is having the size of 4.75 to 9.7 mm aggregate. And we noticed that for GG1 grid, the percentage strength reduction was 10%, while for GG2 and GG3 grid, the strength reduction was 7.5 and 14%. In the next set of tests, we use this aggregate size of 13.2 to 19 mm aggregates, and we observed that for GG1 grid the percentage strength reduction was 18%, while for other two grids it is 14.5 and 24%. Similarly, with the coarser aggregate, which is having the size of 19 to 25 mm, we noticed that the percentage strength reduction was quite high. The percentage strength reduction for GG1 grid was 30%, while for other two grid it is 25.5 and 38%. So it is interesting to note that for the GG3 grid, which is having the smaller aperture and higher number of yarn per unit width, in all the three cases, we can see that percentage strength reduction was quite high. For instance, with this size of aggregate, the strength reduction was very high, which is 38%, while for other two cases also, if we'll compare the other two, it is significantly high. This so that in addition to the aggregate size, grid aperture does matter in terms of strength reduction. The strength reduction in the third case was quite high because the aperture size is very less. So aggregates, when we are using over it, it actually damages the yarns. And this reasoning can be more analyzed using the image analysis which we have conducted. So from this analysis, we can see that we have considered two different grids. So this is the grid having the bigger aperture size, and this is the grid having a smaller aperture size. Both have the intact tensile strength of 50 kilonewton per meter. But after inducing damage, we can clearly see that there are so many numbers of major damages in the grid due to the aggregates which we used during the cyclic loading. And we can see that for the grid with bigger aperture, the number of major damages are relatively less as compared to the other grid. So this shows that due to these damages, when we will do the tensile test, the upper yarns which are damaged will move, and there will be reduction in the tensile strength. In addition to that, due to the minor damages which damage the yarns up to some extent, this causes the non-uniformity in the stress distribution. So whenever there will be a non-uniformity in the stress distribution, the chance of the distortion in the grid will be higher and the tensile strength will reduce. So finally, these are the conclusions of my study. So first is the percentage strength reduction we have calculated, and we noticed that percentage strength reduction is directly proportional to the aggregate size, as well as the percentage strength reduction is inversely proportional to aperture size. So for the grid with higher apertures, the tensile strength reduction will be more. Similarly, from the image analysis, we have noticed that the tensile strength is primarily the damages happen due to this localized damages during the cyclic loading, and we can see this red zone which shows the higher displacement as compared to the green zone, and we can see the non-uniformity in the stress distribution. That's why there is a difference in the displacement of all the yarns. So there is a relative displacement between the individual yarns of the grid. This is the wide width tensile test, and we can see that partially damaged yarn experience maximum displacement above the damages zone, while the portion below remain relatively unstressed. So that is the reason why there is a reduction in the strength. Thank you so much. Okay.
I appreciate your this practical significant work as such, and the forum is open for the discussion. If any question.
No questions? Okay. Thank you so much.
We have a thematic speaker here. So I request our co-chair Professor Ramakrishna Beg to please introduce the professor and invite her for presenting the lecture.
Hello. Yeah. Good afternoon. So it's my pleasure to introduce our thematic speaker, Professor Castorina Fernandez Silva Vieira. If my pronunciation is wrong, please. Okay. So Castorina Silva Vieira is a associate professor at the Civil Engineering Department of the Faculty of Engineering of the University of Porto, Portugal. She is director of the Construction Materials Laboratory and executive vice president of the board of the Institute of Sustainable Construction, ICS. She was vice president of the Portuguese chapter of the International Geosynthetic Society from 2021 to 2024 and deputy secretary of the Portuguese Geotechnical Society from 2020 to 2024. Member of the technical committees of the International Society for Soil Mechanics and Geotechnical Engineering, TC 218 and TC 307, associate editor of the Journal of Materials in Civil Engineering, advisory board member of Environmental Geotechnics and editorial board member of Transportation Infrastructure Geotechnology, Sustainability, Advances in Civil Engineering and Frontiers in Built Environment. So with this introduction, I invite her to make a presentation. The title of the presentation on geosynthetics, tensile behavior after exposure to non-conventional fill materials. May I invite her to make the presentation. Thank you.
Sorry. I didn't sleep, so I'm not sure how it run. How it will run. I don't. One day and a half. Okay, it's working now. So my presentation today looks at the geosynthetic tensile behavior after exposure to non-conventional fill materials. This is the organization of my presentation, mainly connected to the published paper. As all of you know, construction and demolition wastes are wastes derived from construction, reconstruction, cleaning of work sites, earthworks, demolition, and so on. That means that when we talk about construction and demolition wastes, we are referring to a wide variety of substances, of materials, not only concrete and mortars, but also wood, plasterboard, ceramics materials, and so on. Nowadays, the environmental sustainability has been demanding a progressive increase of waste valorization in the construction industry. Construction and demolition wastes should be properly sorted, treated, and transformed, and then transformed in a recycling plant in recycled aggregates. Recycled aggregates, as all of you know, also have been used in roadways applications, come in connection or with geosynthetics. So, one of the main uses of using geosynthetics in ground applications is their durability, and if this topic is important when you use conventional materials, this aspect is much more relevant when we use alternative materials such as recycled aggregates. So, to study the chemical and environmental degradation caused by the exposure to these non-conventional fill materials, small trial embankments were constructed. These small embankments do not have any kind of structural function. They are only built to promote the exposure of the geosynthetics to these conditions, the weather conditions, the climatic conditions, and the time. Additionally, to study the damage caused by the mechanical actions during the installation, laboratory installation damage tests, similar to those presented to the previous speaker, were also carried out. 3 geosynthetics were used for what we refer as a geotextile, this polypropylene geotextile reinforced with high-strength polyester yarns, and 2 geogrids, one with high-density polyethylene geogrid. We call this geogrid as GG1, and the other one a uniaxial geogrid manufactured from polyester yarns, call it as GG2. The selection of these materials was made trying to have values similar as similar as possible of their tensile strength. So the recycled construction and demolition material is a fine-grained recycled material. The predominant constituents of this recycled material are, as you can see here in this table, concrete and mortars, unbound aggregates, natural stones, and also, as you can see here, a significant portion of soil. In this graph, we show the particle size distribution. As you can see, the natural soil is used in this study is finer than the recycled aggregate, and obviously is not a material typically used in the construction of geosynthetic reinforced structures due to its high fines content. Trial embankments were constructed, as I mentioned before, to study the potential chemical and environmental degradation induced by this recycled material and also the natural soils. Again, these trial embankments were not built to assess the damage during installation, but only the effect to exposure to these alternative materials. This slide shows the different stages or different steps of the construction of the embankments, the cleaning of foundation, the manual placement of the fill materials, in this case recycled aggregated at house or the natural soil. The fill material was placed with care to avoid any kind of mechanical or mechanical damage during construction. Lightweight compaction was also used. Then the lateral slopes of the embankments were protected with a coarse recycled aggregate, and then we wait to have some kind of degradation. Here I showed the picture of the embankment after 12 months. We can see here some plants around the embankment. After 6, 12, and 24 months of the embankment's construction, the samples were carefully exhumed to avoid any kind of additional damage. Laboratory installation damage were also carried out. We used a laboratory prototype developed at our University of Porto, composed of a steel box of 300 millimeters a box square, and this box is filled with, in this case, with the recycled material, and the geosynthetic is placed at the middle of the eighth. Dynamic loading with amplitude ranging from 5 to 500 kilopascal at this frequency, and for 200 cycles were carried out or induced in these materials. Then we also performed tensile tests. The tensile tests were performed in intact specimens as supplied by the manufacturer. Were also performed tensile tests in immediately exhumed specimens to isolate the effect of the construction of the embankment from that of the exposure to the fill materials. Tensile tests on specimens exhumed after 6, 12, and 24 months of exposure were also carried out, and also for damaged specimens in laboratory. For each condition, 5 specimens were tested, and the tensile tests were carried out for a strain rate of 20% per minute. This slide shows a picture and the detail of the specimens exhumed of the geotextile exhumed from one of the embankments. The geotextile was damaged only by plant roots, and other damages were not visible to the naked eye, nor in SEM images. Here we have SEM images with an amplification of, I think, is 500. I'm not sure. And here you can see the polyester yarns and the junction of this polyester to the geotextile. This image refers to intact specimens, and the one to the exhumed specimens after 12 months of exposure. And we can see, we don't see any kind of damage as expected in the polyester yarns, even if they are less aligned. They are more spread in the geotextile. Here I also include the graphs of the tensile force during the tensile tests. This for exposure specimens, and this from intact specimens. Here the details of the results, the mean values, as well as the confidence interval of 90% for a T-student distribution. These slides show the results for the GG2 for exposed specimens, exposed to soil, and intact specimens. As you can see, we notice here a greater variability in the results in the exhumed specimens, particularly those exposed to construction and demolition wastes. In this slide, we compare the mean curves, the mean tensile strain curves for the geotextile, the GG1 and GG2. For intact specimens, the black curve, exposure to to construction and demolition waste, the red, and exposed to the soil, the blue ones. As you can see, the reduction in, we can see a significant reduction in the tensile strength and in the corresponding strain in the geotextile. We also note here a slight increase in the geotextile stiffness for strains lower than this evidence, so this increase in tensile stiffness may be attributed to the presence of fill materials that remain attached to the geotextile. Regarding the GG1, the variation of tensile strength is minimal, as you can see, and we have the same similar conclusion here for GG2 for the other geogrid, and we notice that the exposure to soil, the blue, or to the construction and demolition waste has very, very similar effects. Now comparing the average values and 95% confidence intervals, assuming a student's T distribution for the tensile strength, the corresponding tensile strain, and here the stiffness for a strain of 2%. Looking to this graph, we can see that the geosynthetic that showed the most pronounced degradation was the geotextile. Regarding also the tensile strength, the exposure of the geogrids to the soil, the green one, and to construction demolition waste had very similar effects on the geogrids. With exception also of the geotextile, the exhumed geogrids falls within the confidence interval. As we can see, these results fall within the confidence interval for the T students distribution. Here, for instance, regarding the tensile stiffness, the variation are of limited significance, so there are no significant effect on the geosynthetic tensile strength. Again, we can see that these mean values falls within the confidence interval for for this parameter for the intact specimens. We can notice here. Now, the results of the damage due to compaction. So, during the trial embankments construction, as I mentioned before, lightweight compaction was adopted to minimize the damage. The idea is to minimize the damage during construction, to isolate the effects of this exposure to CDW and to the soil from those of damage during installation. Some geosynthetic samples were exhumed immediately after the construction, and additional mechanical damage during installation, as I mentioned before, was also carried out with the construction and demolition waste as film material. Here I present the tensile strength curves. I noticed that one is missing now, the one related to the immediately exhumed samples, but I have the results in the other slide. Here I show you a picture of a sample of damage in the lab, and you can see that apart from the particles that remain adherent to the geotextile, the specimen or the sample remains like intact. Now here I have the results for the four conditions: intact, exposed to construction and demolition waste, damaged in the lab, and immediately exhumed. As you can see here for both geogrids, the tensile behavior of the exhumed specimens for 12 months of exposure and also for 24 months, I can say, is quite similar to those of the samples immediately exhumed. That this confirms that exposure to these alternative materials over 12 months, a period of 12 months, does not lead to significant degradation in their mechanical behavior. The tensile strength of the geogrid subject to laboratory damage is this one. Was very similar to those obtained from the specimens exhumed after from the embankments. So this one and this one, this one and these are quite similar. And again, the reduction in the tensile strength is more pronounced in the geotextile, as I mentioned before. I must say that this decrease in the tensile strength of the geotextile is likely associated with some kind of changes in the bonding between the polyester yarns and the non-woven geotextile, induced by the handling, exposure to the fill materials, rather than the direct damage of these yarns. What we can see, particularly in some images, is that the polyester yarns are less aligned, as I mentioned before, and less attached to the non-woven geotextile, which may contribute to have contributed to this premature failure. To conclude, is the one that exhibited the most pronounced degradation. The exposure of the GG1, the HDPE geogrid, to construction and demolition waste and to the fine soil resulted in negligible effects on its tensile strength. The same for the polyester geogrid, where I can say that the maximum reduction in the tensile strength was around 7.5%, and when exposed to soil. The tensile strength, the tensile behavior of the geogrids exposed to the recycled materials for 12 months was very similar to that of the specimens exhumed immediately after installation. A similar to the recycled material and to the quiet sand or the fine soil were quite similar. And to finish or to conclude, for the HDPE geogrid, the laboratory damage tests were more adverse than its exposure to construction and demolition waste, while the inverse trend was observed for the geotextile. Thank you very much for your attention, and I must acknowledge to these institutions and companies. I'm not sure if I fulfilled the time allocated to me.
No, no, it is on the time. So it's very nice to see the effect of geogrids on construction and demolition waste. Usually we see on the soil, but not seen many. So is there any question for her, please?
Only a question. Your study is in short-term behavior.
Yes.
What you are talking about reinforced structures with geosynthetics, and we must have in mind that these structures must last at least 30 or 50 years. What is your idea about the influence in the long-term behavior of the geosynthetics? That is the more important in this.
I don't bring these results here, but as you know, probably, I'm not sure because I think the results are already published. We also carried out creep failure tests on exhumed specimens and on intact specimens. And what we can see is that even for the geotextile, the exposure of these materials, or particularly for the geotextile, increase their stiffness. Because the fill materials of the fine particles remain glued to the geosynthetics, and means that the stiffness of the material, even for long term, is higher for the exhumed specimens. But we are also studying the effect to the long term. I didn't mention that, and I don't mention that this is only part of a broader research study. I only bring a very small part of the study.
Good. What are the normal operating strains on geogrids and geotextiles in field applications?
The normal
Operating strain levels.
We're
not
quite below the maximum tensile strength.
Yeah.
Around depends on the deformation, the lower, but between 2% or around this.
I would even say maybe 0.2 or 0.3%, maybe 0.5%. So it'd be interesting for you to look at what the effects were, if there were different effects at those strain levels, because that's, the tensile, by then your structures failed and you're no longer interested whether it was soil or CDW. So it'd be good to go back and take a look at the what's happening at the lower strain levels.
We checked it at 2%, but we noticed that for a very small strength, the material remains stiffer than the intact material, but doesn't fail for these values.
Hi, it's me. You have shown in your experimental study you have used a very small plate compactor, but in actual practice for a construction of a structures, everything, they use a very heavy compactions. Do you see different results in terms of the damage, particularly on the polyester side, when they are exposed to the corrosives or like a very abrasive soils?
As I mentioned, I'm not sure if this was clear. The idea was to isolate the effect of the exposure to construction demolition waste. That's why with construction embankment, at the same day, we remove the sample. So in this situation, the effects of damage should be minimal, since we use lightweight compaction method. Then in lab, we simulated according to the European standard the damage during installation with the cyclic load, but not using pooling beam as mentioned the standard, but using the same material, the fine grain construction demolition steel. I must refer again that we are doing with a fine material like similar to soil. The maximum dimension of this material is around 10 millimeters, 10 to 15 millimeters. So the damage should not be very high, even with easier compaction method.
Okay, thank you.
Friends, we have some our quorum is full now for the presentation, so we'll just stick up to the time limit and accordingly. Next presentation is of Jose Cardio and Maria. I will invite. Yeah, you are there. Yeah. And so just before that, just offer the moment to
Thematic speaker. I request the chair and co-chair to please present the memento to our thematic speaker.
for you, for all the presenters, please note your timing is 9 minutes max, and thereafter we'll take one or two questions so that we can stick up to the time schedule. Thank you. So, Madam, just.
Good afternoon. My presentation is about the effect of metal ions on the thermal oxidation of tiles made by high density polyethylene. So the polymeric, the oxidation of the geotextiles can compromise the performance and the lifespan of the geosynthetics. The oxidation can be promoted by heat and also by UV. Also, the oxidation can be accelerated by the presence of certain catalysts, metal ions. The main goals of this research is to study how metal ions of copper and iron affect the thermo-oxidation process of high-density polyethylene geotextile, and compare the results of with the results of PP geotextiles. So the experimental procedure where at first we used a woven geotextile in with HDPE filaments. Then we degraded it with metal ions and thermo-oxidation. Finally, we studied the reduction of the tensile strength. We take two geotextiles with similar tensile strength and the deformation at rupture. The the degradation test at first exposed the geotextiles, and then we made a successive exposure to the degradation, to the two degradation tests, immersion in metal ions and thermoxidation. So, single exposure, copper and iron nitrate, concentration, temperature, and time. Single exposure and then thermoxidation, using these conditions for thermoxidation, 150 degrees temperature, and 14, 28, and 56 days. And finally, successive exposure, copper nitride, iron nitride, and thermoxidation. One note, the samples in single exposure were washed with water, dried, and then tested for tensile strength. The immersed samples followed the thermoxidation in case successive exposure were not washed, so they were contaminated when they are submitted to thermo-oxidation. Here we have, you all we know the result of the tensile test, the curves of tensile test. We use the HISO 13934, and the residual strength is the relation between the tensile strength of the exposed specimen and with the version specimen. The main results, we can see here that the single exposure in metal ions solutions didn't affect the tensile behavior of the geotextile one. But the thermoxidation test had notable impact, so they increased the tensile strength. We can see here the tensile curve for the after iron nitrate intact and iron nitrate solution, and then thermoxidation. In successive exposures, we see that the copper nitrate had no influence in the thermoxidation resistance, and so iron nitrate also did not influence the oxidation process of geotextile 1. So for geotextile 2, we have similar behavior when we did the immersion and followed by the thermoxidation tests. In the case of geotextile 2, single and successive exposure, we see the similar behavior as for geotextile 1, and on the opposite to that what occurred in HGPA geotextiles prior immersion in iron nitrate, we saw a reduction in the oxidation resistance of PP geotextiles. So we have here the behavior of PP geotextiles, and there the behavior of HGPA geotextiles. Finally, we can say that the isolated action of the metal ion solution did not result in the noticeable change in the tensile behavior of AGPE geotextiles. On the other hand, we note change when those geotextiles were submitted to thermo-oxidation tests. This is increasing the tensile strength and elongation, and so reduction in stiffness. The successive exposure to metal ion solutions and thermo-oxidation did not cause additional change for the case of AGP geotextiles. So under the studied conditions, metal ions of copper and iron did not don't accelerate the thermo-oxidation process of AGP geotextiles. When compared to the PP geotextiles that were tested in similar conditions, the IGP geotextiles were much less affected by the action of metal iron in the oxidation process. Future research will explore how different metal ions, copper, nickel, manganese, and zinc affect the oxidation resistance of PPPA and PET geosynthetics. Thank you very much. I hope my time was.
Thank you, Lord. So, any questions, please? Thank you.
Very clear.
So next is performance of double twisted mesh and acidic conductor. Anishu.
Good afternoon, and I would like to thank the organizers for this opportunity to be here. My name is Anisur, and today I have the pleasure to present on behalf of our co-authors performance of double twisted mesh in acidic environment. I was working in Indonesia just before start of COVID and in 2024, so I spent there 5 years. And during that time, Indonesia, which is a country in the Southeast Asia, is a little bit far, so I'll bring you a little bit far from Goa today to tell you about our test, full-scale test we did at the site. We are talking about a mining environment, a gold mine, where we tested the performance of a reinforced geomet for the growth of the vegetation in a very acidic environment. And then we know that in acidic condition, the reinforcement was a steel reinforcement, so that it is prone for the corrosion. And what I have seen is that also in few months, steel exposed to very acidic environment can get fully rusted. So without further ado, let me bring you to the. Yes. So currently we are in Goa, and in a few seconds we'll be flying to Indonesia. Indonesia is a country in Southeast Asia. It is an archipelago. It comprises of more than 17,000 islands, and we are on the area which is a ring of fire. And in that area, those islands are very rich with expensive minerals. And one of those islands, which is the Sulawesi Island, on the northern side, they are very rich of gold mines. So what we did was we were in touch with the mining operator, and we know that when you do the exploration, you need to build, you need to dig, you need to cut some portion of the mountain to build the access road. You can either cut on one side or on both sides. And as you can see, Indonesia is very green. Surrounding is very green. So what you do is you remove the upper portion of the soil, and then you expose the altered rock to the weathering effects. and altered rocks in touch with water leads to create a very acidic environment and soil. The slope were considered stable globally, so there was no need to go for any intervention from a geotechnical point of view to stabilize the slope, whereas the challenge faced by the operator was to mitigate the effect of mining operation by re-establishing green surfaces. So the mining operator, they tested the soil, they took 5 samples from site, and they were tested for any net acidic generation test, and the result from that test showed that the material and the rock that we have at site are having pH ranging between 2.35 to 5, around 5 pH. So what we can say is that we are quite acidic condition, and the target was to revegetate the slope. And the operator tried different methods. Indonesia is a very green country. There is one national standard, which is SKH. I'm not going through the numbers. Just to share with you is that the Public Works Department, so Ministry of Public Works and Housing, they give a recommendation on how to treat the slope depending on the inclination of the slope. So steeper is the slope, the higher should be the performance of the geomat that has to be placed to enhance and foster the growth of the vegetation. So in this case, we followed that Indonesian standards. We explained to the operator that usually this is related to the soil terrain. However, the operator wanted to challenge the effectiveness of a solution that is proven throughout Indonesia, also for their mining environment. And as I was mentioning, we went through geomet, reinforced geomet, because of the considered steepness of the slope, which was reinforced with the double twisted steel wire mesh. And the steel exposed to acidic environment is prone to corrosion, so there was a requirement to provide advanced coating to the steel wire mesh in order to protect. And based on the recommendation from BBA, that coating allows for to expose that coating to soil with having pH between 3 to 13. So we were quite sure that it's going to be performing well, but we wanted to test it. Then another challenge is in Indonesia is that it's on the equatorial area, so we have quite a challenge related to the UV, as well as in case there is any localized dent or damage on the polymeric coating, we wanted that corrosion to not spread too far. So there are a couple of tests. There is one test related to ASTM that talks about corrosion spread. So we also look into these aspects. Then, once we have identified the system and the solution suitable for this site condition, we went through the method that is followed in Indonesia. So we have the reinforced geomet. In Indonesia, they call it taplok method. Basically, you have a mixture of fertilizer, soil, seeds, something that enhance at the initial stage and provides nutrients for the root of the initial plants that are germinating there. So what we can see is that once the operator has identified a site typical for their condition, in a few weeks we have the growth of the vegetation, and in just 1 month we have a full growth of the vegetation, which is fostered thanks to the nutrients that we have in the soil. And then we were observing the performance of the vegetation. After a couple of months, the plants start to perish. The nutrients were no more sufficient because they are required to be there for the initial stage, so that once the plant will grow, they will be, spreading throughout the slope, and it will create a positive environment for the further growth of the vegetation. So we wanted to, I've seen other papers, we wanted to check for 12 months how that performs, and then after 12 months we exhumed the reinforcement netting in order to check how that advanced coating has protected the steel wire mesh. So we went through different laboratory tests. The first one was to check if there is any variation on the thickness of the steel wire mesh, comparing to the, let's say, virgin or just out of factory material. Based on our check on the thickness, we have seen that there was no difference or no reduction, no red rust outside the coating, so that we are having no reduction on the thickness of the steel wire mesh. Okay, so let's look at also the second aspect, which is related to the performance of the netting, not just the only single steel wire. So we have again checked following the international standards. In India, there is also an Indian standard, which is IS 16014, which has been released recently. There is one new update on 2014. And we checked the longitudinal tensile strength, and we found that the results from the exhumed material are in line with the value record that we have for the fresh material. So what we can see is that there is no difference or reduction in tensile strength thanks to this coating that has protected the steel wire. So to conclude, 9 minutes, right? To conclude, when we deal with challenging environment like the gold mining, where we have to deal with infrastructure that needs to be long-lasting, because of course we are talking about people who go there, so people needs to have infrastructure that protect the people and also the infrastructure at the mine. We need to consider in mind the long-lasting solution, and also to minimize the mining operations. To protect the workers, we need to consider some advanced coating that I was mentioning, which can be also used, for example, if the slope is not stable, in collaboration with soil nailing. So you have the netting, you can combine with soil nailing to stabilize the slope, and then the durability. So earlier, one professor was asking about what is the design life, I guess. What is the performance after 30, 40, 50 years? So that aspect is also definitely to be considered. With that, I would welcome any question from your side. Thank you.
Thank you. Any questions?
So thank you so much. It was a wonderful presentation. So my question is, in such harsh condition like city or where the sulfate is very high in the soil, in place of using that steelness, why can't we look for some other sort of grid, like maybe natural fiber just geotextile? Because at the end, we are doing that polymer coating protect. And if we do the same thing with that natural grid, maybe that will also be durable. So why can't we replace with that?
Thank you very much. So, as I was mentioning, we were following the Indonesian standard, the standard that they follow in Indonesia, and for the reinforcement, for the steepness of the slope. So we have a slope which is more than 60 degrees. The tensile strength requirement was satisfied by the steel wire mesh, and then that's what was also commonly used for Indonesia as a approach. They tried also other method, hydroseeding. They tried also using geotextile as a base for the growth of the along with hydroseeding, but it was not performing. So the mining operator was looking for different method in order to find what could be the right best fit for their site.
And one more thing was that for polymer coating, so what sort of polymer actually is it possible to use?
Yeah, you have different type of polymer in the market. There are common market names like PVC, PA6, and so on. So if you refer to the Indian standard IS 16014, there is one which is called high abrasion resistant polymer, and there are rather than defining the nature of the polymer chain, they define in terms of the performance they need to provide, as I was mentioning, UV resistant, corrosion spread, and so on.
So that was the performer that we pull out.
Okay, thank you so much.
Thank you.
Next is a micro and nano X-rays CT visualization.
Good afternoon, everyone. My name is Nana Yamaguchi from Kumamoto University, Japan. Today, I'd like to talk about visualizing freeze-and-thaw effects on a GCL with nano and micro X-ray CT. So let me begin by talking about research background. GCL is a hydraulic barrier material mainly used in cold regions such as North America and Europe. However, in these regions, due to the recent global warming, the frequency of freeze-and-thaw cycles in the ground is expected to increase, which may decrease the barrier performance of GCL. In fact, our permeability test showed that the permeability of GCL increased with the number of freeze-and-thaw cycles. Furthermore, the differential settlement of diesel fuel tank foundations by freeze-and-thaw cycles increasingly being recognized, which raises the risk of leakage. This risk is supported by the previous findings that cracks formed by freeze-and-thaw can become flow paths for organic liquids such as diesel fuel. So complex mechanisms such as water migration and ice lens formation occur during freeze-and-thaw, and it depends on soil properties. So visualizing these effects help us better understand the barrier performance of GCL. As a method to visualize the internal structure of the test specimen in detail, X-ray CT scanners have recently gained attention. These are the nano and micro X-ray CT we used. By selecting the CT scanner according to the sample size and research purpose, it becomes possible to adjust the observation to the needs, either observing small-scale structures closely or capturing a wider overall view. So based on this background, the objective of this research is to evaluate the barrier performance of GCL by visualizing the freezing characteristic of bentonite and the microstructure changes in GCL after freeze-and-thaw using X-ray CT scanners. In the next slide, I will introduce X-ray CT overview and properties of our study. In this study, we separately scanned frozen clay sample and GCL under freeze-and-thaw cycles. First, for the scanning frozen clay sample, we scanned kaolinite to clarify the freezing characteristic of bentonite. We used freezing stage of nano X-ray CT to scan the specimen with a diameter of 6 millimeters. And next, we scanned GCL under freeze-and-thaw cycles. Since GCL was cut into the disc with a diameter of 50 millimeters, we used micro-focused X-ray CT for the scanning. These tables show the material properties of kaolinite and bentonite we used. Bentonite liquid limit of bentonite is 342.4%, which is extremely higher compared to the kaolinite. So this means bentonite in this study has a quite strong swelling and water retention capacity. Let's move on to the CT method and results. I'll start with case 1, frozen kaolinite and bentonite. This photograph shows a scene of scanning specimen by using nano X-ray CT. We put this freezing stage inside a CT scanner as shown here and controlled this Peltier element at minus 16 degrees Celsius to freeze the specimen in one direction. The water content of both kaurinite and bentonite was adjusted to 130%. Here are the CT scan results of kaurinite before and after freezing. In CT images, lower density areas show darker, so structures like iceland show up dark, while kaurinite shows bright. For kaurinite, we can see the typical layered iceland pattern after freezing. Here are the results for bentonite. After freezing, bentonite showed complex mesh-like icelands along the vertical freezing direction, in contrast to the layered iceland pattern observed in kaurinite. Bentonite has high swelling and water retention properties, which are considered to be the main reason for the differences between bentonite and kaurinite when frozen. During freezing, these properties restrict the movement of water, which is necessary for iceland formation. As a result, it can be said that complex icelands develop vertically within the bentonite. Next, I'll show you case 2, the GCL under freeze and thaw cycles. First, I will explain about the freeze and thaw method. Since micro CT doesn't have a freezing stage like nano CT, we developed a freezing and thawing device with this thermal insultation to prevent the GCL from thawing during scanning. In this device, freezing and thawing starts from this iron bar and spreads in one direction. This iron bar also applies overburden pressure equivalent to 7 kilopascals, which simulates the condition of a GCL placed near the ground surface. Freezing was carried out at minus 16 degrees Celsius, same as in the nano CT observation, and thawing was conducted in a room maintained at 20 degrees Celsius. So in our preliminary experiment, we measured the internal temperature of the GCL and found that each freezing and thawing process required about 12 hours. So we ensured at least 12 hours for both freezing and thawing process in this case. This is a scene of scanning GCL. We scanned the GCL after the first freeze and thaw cycle and fifth repeated cycle. These are the result image of GCL after the first freezing and first thawing. This part is the non-woven cover geotech style, and here is the woven carrier geotech style, and these are the needle punch fibers. And here, these are the image after the fifth freezing and fifth thawing. From the first to fifth freezing, frozen GCL showed a distinct iceland pattern along the vertical freezing direction, similar to the nano X-ray CT results. Furthermore, after thawing, the cracks were clearly visible along the needle punched fibers. These cracks are expected to have a deep impact on the barrier performance of GCL. Finally, here is a conclusion. When bentonite freezes, icelands develop in the vertical freezing direction. This unique characteristic of bentonite remains as vertical cracks in GCL after the freeze and thaw cycles, which could provide propath for fuels and other chemical solutions. I'd like to close my presentation. Thank you so much for your attention.
Thank you, Nana, for your presentation. Yeah, any questions, please?
Thank you for the presentation. So the geotextile we use is the needle punch geotextile. So if I'm not mistaken, the fibers are kind of aligned vertically after freezing. Why do you think the fibers just line like vertically?
Thank you so much for your question. I think needle punch is very important for the strength of GCL. But in this case, so in my opinion, there is a local gaps around the needle punch fiber. That's why the cracks are remaining. So maybe to improve this situation, we need to consider about the intervals or place of Newton's credit.
Thank you, Nana. Thanks.
Okay, so next presentation is on comparison of ASD and LRFD based design of reinforced soil walls. Right? Okay, Deepa Mana. Okay, thank you.
Good afternoon, everyone. My name is Divya. I'm working as a design engineer at TechFab India, Vadodara office. So we do designs of reinforced soil walls, or otherwise called mechanically stabilized earth walls. So just a brief introduction. Reinforced soil walls are internally stabilized earth retention systems having phase inclination of from around 90 to 70 degrees. And these are always retained using some facing which can be blocks or panels, and the reinforcements are provided using either geogrids, geostraps or geostraps. And while designing the reinforced wall, these are the main components we consider. Like there will be a reinforced zone, then the retained fill zone, and facing. And the facing will be supported on a leveling pad, then the foundation on which the reinforced wall is standing, and the pavement above. So while designing the RS walls, we generally consider external stability and internal stability. In external stability, we consider the reinforced zone as a solid block, and we check for the stability against sliding of the wall, of the reinforced block, bearing capacity of the block, and also overturning stability and limiting eccentric stability. And in internal stability, we check for the rupture of the reinforcements, then pull-out failure of the reinforcements, and also the internal sliding in between the reinforcements. So there are actually two main methods currently used for designing RS walls. Up till now, we have been using the allowable stress design method, which is mainly used in ASHTO 2002 code and also IRC SP 102 code. But currently, since all other designs are moving towards load resistance factor design, which is also called LRFD design method, and the new codes, IS codes, are also recommending LRFD method for the design of RS walls. So we use sheets for providing the design of RS walls. So and up until now, we were using guidelines based on, we were using the designs based on IRC guidelines, and now we are moving towards the LRFD design. So I just thought of comparing both the methods using standard software. So just in brief, to compare both the methods, in ASD method, allowable stress method, we check the internal and external stabilities using non-factored loads, and then we derive the factor of safety for each failure mode, and then design the RS walls. And in LRFD methods, the loads are applied some factors, loads are increased by some factors, and the resistance offered by the soil and reinforcement are reduced by some other factors. And we check a factor called capacity demand ratio, CDR, and it is ensured that for each mode of failure, the CDR value is greater than 1. So like this. In ASD method, we use different factor of safety for sliding, bearing failure, eccentricity, like that. And internal stability, we use factor of safety for rupture, sliding, and pull-out. Whereas in LRFT method, we derive for each of these failure modes, we derive factored resistance versus factored load ratio. And it is ensured that this value is greater than or equal to 1. So these are the factors which is recommended by IS code for loads and resistances. So this is the specialty of LRFT method is that depending upon the type of failure, the factors used are different. So for example, for vertical pressure load, in sliding and eccentricity, we consider the factor, we multiply the loads by 1, whereas for bearing capacity, we multiply it by 1.35. Similarly, for live load surcharge, dead load surcharge, everything, we use different factors, load factors. Also, for resistance, there is different reduction factors. I used commercial software MSCW for comparing the designs of LRFT and AST methods. And I did a parametric study for different heights of the RS walls for 2 types of arrangements, blocks and geogrid arrangement and panel and geostrap arrangement. So these are for 3 different heights of RS wall designs for using blocks and geogrids. These points show the length of geogrids at different depths. So this is the topmost geogrid length, and this is the bottommost geogrid length. So from this, the circle shows the design length for from ASD method, and the cross one shows for from LRFT method. So we can see that for for higher heights of the walls, the LRFD is demanding more length towards the bottom of the wall. And for very smaller heights, both the methods are recommending almost same lengths for the geogrids. And on geogrid strength, both the methods are demanding almost same strength for both for the geogrids. Now, as I told, this is because in block geogrid arrangement, we observed that direct sliding is more critical in failure, in internal stability. So we can see that, like in direct sliding, in LRFT method, we are giving for lateral earth pressure, we are providing a factor of 1.5, whereas for vertical load, we are providing a factor of only 1. So because of this, towards the bottom of the wall, it becomes more critical and compared to ASD method. Hence, LRFT method is demanding more length towards the bottom of the wall. Now, we can see that the lateral earth pressure increases with depth of the wall, and so towards here, in direct sliding, the vertical forces vertical loads are having a factor of load factor of only 1, whereas the lateral loads are magnified by 1.5 times. So hence, it is, whereas in ASD method, we are not multiplying it by any factors. So LRFT method is demanding more length towards the bottom of the wall. Now in panel and geostrap, we observed that for all the heights, both the methods are demanding almost same length of the reinforcement. This is mostly because actually in tech strap and panel, the most important, most critical failure mode is pull-out failure of the strap. and which is more critical towards the top of the wall, because the length of the tech strap towards the top is should be higher, because for resisting the pull-out failure, we need to have only this much portion only contributes for the resistance of pull-out. So that is, and since the pull-out resistance is pull-out resistance is calculated as the vertical pressure on the reinforcement into coverage ratio of the reinforcement and the length in the resistance zone. It is dependent on the vertical loads. So hence, there is not much difference in the results in the ASD and LRFT method. So in summary, both ASD and LRFT methods provide require similar reinforcement strength. However, in geogrid block arrangement, more length is required towards the bottom of the ball in LRFT method, and in geostrap panel arrangement, similar lengths are required from both the methods. That's all from me. Thank you.
Okay, thank you for nice presentation. Any questions, please?
I have a question that as you compared ASD and LRFD, so regarding the length of the geogrids, you are saying that for the LRFD we have to provide the greater lengths.
Yes.
So can you define from the slide 10 that we have a general criterion from 0. That length of the geogrid we shall 0.7h to 0.9h.
Yeah.
So in that terms, can you quantify that if possible?
Okay.
Like
That
for
is
that
the
ASD
minimum
it is.
required, but when we do the internal stability, we check each we check for each reinforcement layer whether it is safe against pull-out failure, sliding failure, and rupture for each of them. So at each level we calculate the tension which is acting on each reinforcement, and then we check whether the length is sufficient and the strength is sufficient to take the tension. So towards the bottom of the ball, the tension is higher.
Just my question is just can you quantify between the ASD and LRFD that points that this is the criteria that like 0.7h is required for the
that
ASD
is not
and
like in both the methods they say like 0.7h is the minimum required length.
Ms. Divya, nice presentation, being designer in the RE wall. This is on some different side. Until last few years, we used to do ASD only and structures are still standing and now we are moving towards LRFD. So what is your opinion, frank opinion, whether we should go with the LRFD or not? Difficult to answer. Yeah, actually, yeah, basically we are increasing the loads and decreasing the resistance, and it is the correct observation that the strength length demands are more, but it is a market trend now that everyone is doing with LRFD.
Yes, I think that must be required.
That must be required, but why it is so, from your paper only, why it is so that for block and geogrid where we have the 100% coverage ratio, still there is a difference in demands, and in panel and strap there is no difference, it is continuously coming. So that area we may explore further in your...
Because in strap, it's more critical towards the top, and at the top the lateral earth pressure is, the effect of lateral earth pressure is less. Like in LRFD method, we are multiplying the lateral earth pressures with a factor of 1.5. So, whereas the vertical is remaining the same.
That's okay. I'm just wondering why there are different demands for panel strap arrangement and block grid arrangement. But this can be the area where we all designers can explore. Yeah, thanks.
Now next session is from Shobha Bhatia. It's a dewatering of low solid content based using geotextile strips, incest and direct testing.
Good afternoon, everyone. So my presentation, actually, my team, George Sabre, is the one supposed to be coming, and they're making the presentation, but travel from US to India is not easy. So I'm on behalf of George presenting this book. Now, geotextile tubes are used extensively all over the world, particularly so just to give an idea of what geotextile tube is, it looks like a long sausage, flat. They can be 100 or 200 feet long. They can be diameter of this room, and they vary in size depending on need of the project. Sometimes you need hundreds of tubes, sometimes you need 2-3 tubes to dewater sediment. Now, what dewatering sediment, why do we need to dewater sediment? There are many applications, whether it's a port or in a lake or near a river, where sediments accumulate with time and they need to be removed and reduce the quantity, and sometimes they have taken to landfill and sometimes they can be used. So sediments, when they are dredged from these water bodies, can be very small sediment content, 2 or 3%, particularly in mining. And when we remove the sediments from lakes, they can be 15 and 20% in quantity. So for last 15 years or so, we have been involved with industry working on many different type of sediments. As you can see in the first one is these are not really sediment. It's a pond where the rubber or the glue company has been depositing all their waste, and these are very low, small particles, and the specific gravity is very low, and they are very low solid content. In the middle you see a pond. It's the New York City residential area has a pond. Lot of sediment got accumulated, and they needed to be dredged so that water can have its capacity. And here the sediment solid content is almost 13 to 14%. The last one is a lake, very large lake in the city in Syracuse where I live. And here the sediments are highly contaminated and highly variable with lot of organic content and clay content. So I think what I want to focus that each project can be very different, and in practice generally when remove these sediments, they don't perform any geotechnical test. They take the sediments, slurry, mix different polymer, and then try to see how they can really dewater these sediments. So we worked with a company who provided us sediments from 15 different water bodies in Canada and US, so highly variable in nature. And then we combined with 5 standard sediments, Ottawa sand, very fine sand, some tally which is local area, kaolinite and organic material, and try to understand if the physical property and chemical properties of these sediments has any kind of relationship about amount of dewatering we can do. It was very ambitious because generally this is not what industry is generally doing. And for this particular project, and credit goes to George and many other undergraduate students, because they did all these specific prop measurements, specific gravity, grain size distribution, particle shape, organic matter, specific surface area, and all chemical properties follow of these 20 sediments, ranging from pH to zeta potential and particle charge density. So we had a lot of physical and chemical properties of these materials to really know nature of the materials.
Now, if these are the range of particle size distribution, if these lines are very low, but you can see they have wide range in particle size, wide range. And when we look at this chart here in the middle, which Pi is plotted here, fine content are plotted here, and percentage of organic materials plotted here. This is the scatter of all the sediment which we are testing from many different water bodies. Now, generally, these sediments have significant amount of fines, and these fines, when they are going to be pumped in tubes, which are quite open, geotextile, woven geotextile, they need to be flocculated, otherwise a lot of fines will come out. So 99%, I would say, in projects, polymers are added, and these polymers are typically polyethylamide, ranging from cationic to anionic. So we selected number of polymers, and for each sediment found out what is the really best polymer which can make the particles, lump them and make them flock. So now you have a larger particle, it's not particle anymore, it's flock, and which can be retained on geotextile when we will dewater. One of the tests we have developed over the time is called a centrifuge test. This is a very standard test used in chemistry or chemical engineering, where you take a small bottle of a slurry, you put in the centrifuge, and you're rotating it in very high frequency and rotation. And after that, decreasing in height, the sediments are consolidating, and then you measure the consolidated height of that. And then from that, we predict what will be the solid content. And we have found they are generally large in the field, but that only is done when the project is approved. But many times in the beginning or starting of the project, you want to have an estimate of how much work is or how effective this technique is. So for this research, for all sediments at different water content, these tests are performed. So here I show you results for standard 5 salts, which is kaolinite is here, and then organic salt is here, which is standard, and then these are two fine silt sediment and autwa sand. So you can see as the particle size is increasing, these curves are shifting this way, which means that after dewatering, if we start all the sediment with 10% solid, sand definitely is going to dewater a very high percentage solid, almost 60% solids are there after dewatering. Whereas kaolinite, after centrifuge or dewatering, it will be only 35%. But for that, we have to do the test. And one thing is important to see what we call yield stress, which is Py. That gives you an idea of what is the final solid content. And you can relate this Py value to really the percentage solid, and this is called a gel point. So I'll show you some data about gel point, and this is what industry needs in the field. Okay? When they claim, when they bid for a project, and you get a slurry, and they need to predict in the field what will be the solid content that will be achieved. So here are the test data for all these 25 or 50 sediments, and we don't even know the nature of the sediment. They vary widely. And when we look at these using this equation and looking at yield stress versus the slope, we make an observation, clear observation. As the fine content in the slurry increases, the yield stress changes as a function of that. And then we found that important parameters are really D10 of the salt, specific surface area, both are interrelated. Finer are the particles, so we can find that this is the equation we came up with our large amount of data. These are measured gel points from centrifuge test. These are calculated values and reasonably good relationship. How can we use this? What is the value of that? Well, if we know the D10, which is grain size distribution, specific surface area. These are simple tests to perform, and using this value we can estimate what will be the gel point or percentage solid in the field without doing a large scale test. Okay. And but we found that in this test study that lot of chemical properties, we measure many chemical properties, most of the chemical properties had no relationship. They are definitely affect type of polymer we select and amount of polymer, but nothing to do with solid content. They were more related to physical property of the material or sediments. So finally, conclusion is organic matter, specific surface area, and fine content are important. We work with the industry which does very large projects. They still don't measure these properties, but at least they give an idea. Once you have sediment, you should pay attention to do that. As I said, that many of the chemical properties had very little effect on that. Now, this conclusion is based on 20 sediments, but extensive testing was done. We were hoping that we will find more relationship with chemical properties, but unfortunately we did not. I'd like to acknowledge, of course, George, for his degree, he did all this work. There were a large number of undergraduate students who did a lot of testing in the lab, and then all the sediments, buckets and buckets of sediment came from our company, Water and I'd like to thank their support. And thank you for your attention, and I'm happy to answer any questions.
Thank you, Madam. Any question, please?
Thanks. Okay. So next in the schedule is achieving SDGs through geotextile tube dewatering system in South Africa by Nikhil Udai.
Good day, everyone. My name is Nikhil Udai, and I'm a civil engineer specializing in sustainable infrastructure solutions. Sustainability and the solution that can remedy this problem. We'll then journey through some technical insights like the soil to geotextile interaction and a few other concepts. So this study draws on research conducted worldwide, and based on this, a roadmap for implementation is conducted to seamlessly integrate this solution into tailings management systems. And lastly, we'll conclude with the overall sustainability and impact of this solution. So South Africa produces roughly as a resource. So the question is, why are we still burying what the world is filthy with? So when it comes to tailings waste, our default solution has been to design, build and operate tailings storage facilities. And yes, while designing them may be complex, they represent the easier human choice: discard, contain and move on. But as we step into the future, shaped by the UN's SDGs, this mindset is no longer enough. As professionals in this industry, we are called to think more mindfully, not just how we contain tailings, but how can we treat them and reuse them as a resource. Mary Spreight in 1994 showed South Africa the devastating consequences of tailings dam collapses. Lives lost, communities displaced, and land destroyed. But fast forward 20 years and you see the same story in Canada at Mount Holly. Millions of cubic South African issue. It's an international problem. It's an international problem that focuses on environmental, social, and economic consequences. And if it can happen in South Africa, so here's how they work. In the filling phase, fly ash is pumped directly into large, high-strength permeable tubes. Polymers are often added to improve the particle separation and bulk up particle size. In the dewatering phase, water drains out through the fabric pores by gravity. Finally, consolidation phase, the material densifies into a stable, compact mass. So let's look at a few technical insights into this solution. Dewatering fundamentally changes fly ash. First, particle size and polymers. Fines flocculate into larger aggregates, shifting the material towards well-graded sills or low plasticity fines. Second, compaction. Dry densities of up to 1.2 to 1.6 tons per cubic meter and moisture contents between 18 and 30% make it viable for engineered fills and road sub-bases. Third, shear strength, cohesion values. These range between 5 and 25 kilopascals and friction angles between 18 and 30 degrees, on par with marginal soils, which allow for use in non-critical layers or confined applications. Fourth, permeability, and this is closely comparable to silts. It effectively limits leachate migration while aiding drainage control. So these properties enable applications in sub-bases, lightweight embankments, blended cements, replacing up to 30% of Portland cement, and even flood defenses when integrated with geotextile tubes. The geotextile allows water to drain while solids are trapped. To improve efficiency, polymers are added. They bind fines together into larger aggregates, improving retention and preventing clogging. Therefore, when we look at mechanisms of action, we speak about the filtration and retention properties, the hydraulic behavior, and the polymer conditioning involved in this solution. Once filling starts, consolidation happens almost immediately, unlike ash ponds, which can take up to decades. Stability depends on the design. Fabric resists pressure inside. Friction holds stacked tubes together in place, and a prepared foundation prevents settlement or seepage. The main long-term risk is clogging. However, this can be managed with the right polymers, as my previous speaker mentioned or touched on. And finally, tubes must always be placed on an engineered pad with liners to stop leachate from seeping into natural grounds and meet regulatory standards. Okay, so globally, fly ash is treated as a resource. Germany recycles over 60% of this into cement, road and embankments, while China reuses nearly 70% of it, mainly in bricks and soil stabilization. South Africa, by comparison, produces 30 million tons a year and buries over 90% of this. So this study produced a roadmap for implementation, showcasing how this solution can be seamlessly integrated into tailings management systems, from lab benchmarking to pilot demonstrations. So geotextile tube dewatering is more than just engineering. It's sustainability in action. Reducing risks, recovering resources, and creating economic value. It directly advances the SDGs by turning waste into an opportunity and shifting us from containment to transformation. Okay, and that brings me to the end of my presentation. I will now open up the floor for any questions. Thank you.
Thank you. Any question, please?
Presentation.
Thank you.
So fly ash also have heavy metals. So is that not a concern because you have to be very careful with these things?
Yes, so it is a major concern, and that's why polymers are added. This research or this topic is part of a broader research topic, and the bigger concept is to create synthetic structures out of these filled tubes. So you're not actually cutting open the bag and reusing the material, but creating synthetic structures out of these tubes. So as much as it is a problem, with the addition of polymers, and you will have a final product which is a filled up tube. Yeah, so as much as it is a problem, we have done some research into the heavy metals that's involved in fly ash. I know in South Africa we have class F fly ash, and that has quite a lot of heavy metals in it. So part of my research is to find the right polymer for the right amount of fly ash. So for me specifically in this research, I'm looking at South African fly ash.
So are you looking into beyond the polyacrylate other polymers?
Polyacrylate will be the starting point, and if that doesn't work, then we would have to look at other options. But that is the starting point.
Following the previous question, how do you think the use of fly ash can contribute to the Sustainable Development Goal 6? The one related to clean water.
Water. So recovering the water that's used in dewatering the fly ash itself. So collecting it and using it for different applications, whatever site that you are dewatering at, using it for watering gardens or washing cars or anything like that. But yeah, this topic here focuses on different aspects of the engineering world, whether it's the chemical side of it, whether it's the civil side of it, mining side of it. It's quite a broad topic. But,
Okay, thank you. Thank you very much.
Okay, thank you.
Just checking that whether Saurabh Gas and Shivani Viste has reported. Have they reported? No. Okay. So now next is our own instrumental personality from IIT Vishal Teja. Let us begin.
Very good evening, one and all. Myself, Vishwa Teja. I am coming from IIT Bombay. I am a third-year research scholar. I am working with Professor V.V.S. Vishwanathan. We work in National Geotechnical Centrifuge Facility. So my work is about geogrid strip reinforced soil walls when subjected to rainfall. This would be the contents of my presentation today. Need for study, geosynthetic reinforced soil walls, coverage ratio, backfill specifications, then the centrifuge test results and conclusions. Coming to the introduction part, we are at a very high rate of urbanization that is taking place. So when we discuss about urbanization, the first thing that comes to our mind is networking, road networks being developed. And when road networks are being developed, we have an issue with space. We don't have that much space in the cities, or now in fact in lesser towns and all, where we cannot go for embankments which are wide enough, which they used to be. Now we need more vertical walls. So going for a conventional retaining wall would be costly, and it would be more time taking compared to our reinforced soil walls. And need for the study, I am actually targeting to reduce the reinforcement through making it discontinuous, keeping the coverage ratio less than 1. That is the area of research over here. And the second point is the alarming trends of rainfall. If you had observed, this August 2025, this was the wettest August in the past 5 years. So the rainfall trends seem to be changing compared to the last 5 years. And if you see to the prediction, to the comparison that is given with the last decade, there is an increase in 30% in the rainfall. And another issue what we are targeting is the scarcity of suitable material. Code would say very rosy material, saying that the fines should be less than 15%, it should be free draining material, all these things. But the fact is that we are not finding such material. We are on the verge of finding such good material. So we have to find alternatives to use the material that is available and make structures which are performing and sustainable. So that's the target. This actually one of the one of the co-presenters have already mentioned about an RE wall in detail. I did not discuss much about it, but in short, I would like to make it three important components of an RE wall. One is the fascia, the reinforcing element, and the reinforced fill, backfill in general. So out of these, when I talk about reinforcing element, when I'm talking about strips or strip reinforcement, we need to discuss about coverage ratio. This relation between coverage ratio, which is the width of the strip, to a horizontal spacing, a specific horizontal spacing, this has already been established, well established. But in the recent code that has come out, Indian standard, they have presented a different code which is more site specific. I would say which is more site specific and more common to the field, where we have aspects something like N and M. N and M are the number of connectors, and M corresponds to the number of strips that are coming out from a connector. Now the common orientation, if you see to the left, the common orientation, we have two types of orientations fundamentally. One is parallel to the facing, and then we have a zigzag version. Zigzag orientation is not actually represented in any of the codes, but IS code recently it has given a zigzag orientation as well. So when it comes to zigzag orientation, there should be some arrangement in a way that this reinforcement is connected to the panel. So that arrangement will make this connector N, and how many loops it is taking, the strip reinforcement, that will make the N. And B panel is nothing but the average width of the panel. It starts from around 1200 mm and it goes up to 2000 mm. The panels are the width of the panels are different in specific to different conditions. Yeah, this is one more thing. Like I was telling, three important aspects: fascia, reinforcing element, and the backfill. Fascia, reinforcing element I've just discussed. These are the backfill specifications that are given by various codes that are there throughout. And in most cases, our focus of interest is it should be 15% or less. But when I've tried to gather some field case studies and trial pit materials, it is astonishing that in most cases the fines were found to be more than 20% or 25%. So this combination, the rainfall and a backfill which is not actually draining, that's a very difficult combination to handle for these kind of structures. So these are some of the case studies that were reported when the backfill is having a higher fines percentage and the rainfall is affecting it. One recent publication that was given by Dasaka and Raghuram 2024, where they have used fly ash as the backfill material, and they forgot to modify, I don't know whether they have forgotten or they updated the design. They forgot to change the filter material. If most of you know, there is a filter drainage material right behind this, and there is a geotextile wrapping that is behind that, so that the water gets freely drained, so that the fines remain in position. The AOS of the geotextile was not properly selected, so that you could see the fly ash material coming out through the spaces of the panel. This was the case. Yeah. Centrifuge facility. This is the National Geotechnical Centrifuge facility at IIT Bombay. Capacity is 250 G ton, and it's a beam centrifuge, large beam centrifuge with a radius of 4.5 meter, and we can have a model area for 1 meter to 1.2 meter, or we can go up to 0.76 to 1.2 meter. Coming to the model test that I've conducted, these are the schema or the specifications. Fundamentally, when we do a centrifuge test, we need to focus about the scaling laws. We need to reduce everything in terms of a particular scaling law, whether it be rainfall, whether it be the geosynthetic material, whether it be the panel, whether it be the flexural strength of the panel, whether it be the dimensions, everything to be scaled down. So these are some of the comparisons that I have given with respect to the tests that I have conducted. And to the right, you can see the cross section and a schematic plan view where how the reinforcements have been laid. And you can see over here, this is the rainfall setup that we have created. It was already developed in our laboratory. So employing that, we tried to create a rainfall of 10 mm per hour, prototype rainfall. 10 mm per hour, IMD says it is moderate rainfall. So we tried to target that. And another reason is that we developed a sand kaolin model, sand kaolin mix, laboratory developed, which is 4:1, 4 parts sands to 1 part kaolin. And when we tried to bring the grain size distribution, we can see we have a 20% fines, which is slightly above than the stipulated. So it actually suits our marginal backfill or a low permeable backfill. That's what we were targeting about. And like I was saying, when we are trying to find out the permeability characteristics, it's at 10 power minus 6. And when this is rainfall intensity is about 10 mm per hour. There is a parameter called I by Ks, which will actually define whether the rainfall is being infiltrated or is it being transferred into runoff. So we want the effect of infiltration rather than it being a runoff. So that's another reason why we have targeted at 10 mm per hour. There were previously tests that were done with higher intensity, but eventually most of it was runoff. It was not infiltrated into the body. This to the left you can see this is the model geostrip that we have procured, and actually we have identified and made it into a strip. And for all the models, we have something called as a stencil, so that we should know what is the specific distance between two strips, so that the coverage ratio can be maintained. And whenever this coverage ratio aspect comes, it is always center to center. If it is geogrid, full reinforcement, then it can be in a different duration. But in this case, it needs to be, the edge strips should be half. This is the model test package that we have. A water tank, 20-liter capacity, which can actually, which is operated by a solenoid valve. Solenoid valve is an electric switch. So operating that, we can turn on, turn off rainfall. And this is the rainfall nozzle stack. Then this is the wall. What we do in addition is that we capture the photographs at a regular interval. It's about 5 seconds we take a photograph by help of a GoPro. Using those photographs, we do the analysis after that. I'll be showing that. This is the cross section, and this is the 6-layer orientation, 6 layers of reinforcement orientation that is placed in the model. This is before, while we are compacting the model. And this you can see the nice animation of all the GIFs collected. That's how it eventually failed at about 10 days. This is the exhumed geostrips. These are the deformations. These are some of the surface settlements and phase movements that we have seen. Water pressure developments, displacement contours. These are the strain matrix. Coming to the conclusions, the wall that we have tested for 0.5 coverage ratio, it has failed at 10.24 days of rainfall. The coverage ratio that we usually select in the field, it starts around at 0.45 and it goes up to 0.7, 0.8. But the lower bound, whatever we are using, 0.5, it is not actually standing for a rainfall of 10 mm or not more than 10 days. So we have got some observation results. Maybe this 0.5 coverage ratio would be suitable for a fines content less than 15% or maybe with even less. When the fines content is increasing, 0.5 coverage ratio would not be sufficient. After this, we did some higher coverage ratio test as well. Soon we will be publishing that. Thank you.
Thank you, Vishnudev. Any question, please? I hope we are in time now. Almost it's the time, closing time. Thank you, Vishnudev, and thanks all participants, those who have presented, attended, and really it was great work. On behalf of IJ, Geotech Asia, we really appreciate your initiative, and thanks once again. Thank you.
Can we have a group photo with all the presenters?
Yeah, it would be on the remote. On behalf of the organizing committee, I would like to present this memento to our chair today, Dr. Isaac also a moment of appreciation to our co-chair.